So now this is the second part of this lecture, and I wrote here what we need to prove. So here is the context. We have an array x tilde and j of independent random variables. J it's running between 1 and kn, and I always forget to say that kn it's converging to plus infinity. And we have two further assumptions on this sequence. They are uniformly negligible, which means that for all epsilon, the limit of the maximum of the probability that x tilde it's larger than epsilon goes to 0. And this sequence, instead of the previous one, the original one, has a property that there exists a finite constant C0 for which a tilde and j it's bounded by this constant times the probability that x tilde is larger than 1/2. And a tilde and j here is this expression where mu x tilde and j is the distribution measure of the random variable x tilde and j. Then we define the Poisson transformation of parameter 1 of these variables. We represent them by y tilde. And what remains to be proved is the following proposition. Assume that there exists a sequence of real numbers such that the sum of x tilde and j minus an is converging in distribution to S. We want to prove that the sum in j of y tilde and j minus an is converging in distribution to the same law. So this is what I'm going to prove in this second part of the lecture. And we have seen in the first part of the proof that if we wish to prove this convergence, it's enough to show that for all delta positive, there exists a C delta finite, such that this sum it's bounded by C delta, and B, that there exists a finite constant C0, for which this sum it's bounded by C0. So I will prove in this second part of this lecture conditions A and B from the assumption that x tilde and the sum of x tilde and j minus an is converging distribution to some law. So this is the content of the second part of the lecture. So I rewrote here the two statements we need to prove. And before we start proving these two statements, let me do some remarks. So the first remark, it's very simple. Let me consider a random variable x, and let me introduce a new random variable, which is represented by x prime, whose distribution is exactly the same as the one of x, and which is independent from x. Now what I claim is that if you consider the characteristic function phi of the random variable x minus x prime, this characteristic function it's equal to the one of x, phi x, t, in which you take the absolute, well, the norm square. And we proved already this identity, but maybe let me prove it again. So by definition, the characteristic function of x minus x prime is exponential I t x minus x prime. Since these variables are independent, we get this expectation it's equal to the product. The first piece is the characteristic function of x, phi x of t, and then we have the expectation of exponential minus I t x prime, but since x prime has the same distribution as x, I can replace x prime by x. Now you see that exponential minus it is just the convex conjugated of exponential itx, and the expectation of the convex conjugate of a function, it's equal to the convex conjugate of the expectation. So this is equal to phi xt times phi xt, the conjugate, and this gives me this identity. In particular, the characteristic function of x minus x prime, it's always a real number. So this characteristic function takes value on R instead of the complex plane. So this was my first remark. Then I have a second remark, which says the following. Well, assume that you have a sequence of random variables Zn, which converge in distribution to some random variable S. Now consider again, a new sequence, which I will represent by Zn prime, which is independent from the first one. So Zn prime, it's independent from Zn, and has the same distribution. What I claim now is that, well, Zn minus Zn prime converge in distribution to a random variable whose law is equal to the law of S minus S prime. So here I would take an independent copy, say, of S. So I'll take a random variable which has the same distribution as S, but which is independent from S. I construct this new random variable, and the claim is that Zn minus Zn prime converge in distribution to S minus S prime. And this is almost a trivial consequence of the first remark, because let me consider, to prove convergence in distribution, it's enough to show that the characteristic functions converge pointwise. So let me consider the characteristic function of Zn minus Zn prime at t. We have seen that this is equal to the norm of Zn t square. Since Zn converge in distribution to S, the characteristic function converge, and therefore its norm converge. So this is converging to f phi S at t square, and this holds for all real t. And now, well, this is exactly the characteristic function of S minus S prime of t, and therefore we have proved that the characteristic function of this sequence converge to the characteristic function of S minus S prime, and that proves by Levy continuity theorem that indeed Zn minus Zn prime converge in distribution to S minus S prime. Now, third remark, and last one, the assumption of our proposition is that the sum of x and j minus an converge in distribution to a random variable s. Now let me define u and j as x and j minus x and j prime. So you see that I'm taking here a copy, x prime and j, which is independent from all random variables x and k. And x prime and j has the same distribution as x and j. And now I'm defining u and j as this difference. We have seen that in remark 2, that if we have a sequence which is converging distribution, this means that this sequence, which is the sum of x and j minus an, minus, if I take the prime version of this quantity, but the prime version of this quantity is x and j prime minus an, because an it's a real number, so x prime, if x prime it's independent from xn, x prime minus an it's independent from xn minus an. So by remark 2, this expression it's converging in distribution to s minus s prime. But if you take the difference, you see that the an cancel, and what you get is that the sum of u and j, it's converging to s minus s prime. So this is the condition I will use in order to prove A and B. We know that x and j minus an is converging distribution to s. If we define u and j as this difference, where I repeat x prime and j is independent of all random variables x and k, and they are independent also among themselves, and x and prime and j is independent from x and j. So let me write what I want to say exactly, precisely. So what I'm saying is that this set of random variable x and j, x, and there are tildes here, of course. I forgot all the tildes, but I won't put a tilde in u and j to keep notation simple. So what I want to say is that these variables, k, for j between 1 and kn, and k between 1 and kn, that this whole family, it's a family of independent random variables. And moreover, x prime tilde nj has the same distribution as x tilde nj. So this set, it's a set of independent random variable, and this random variable has the same distribution as this one. It follows from these two conditions that u and j, and now j going from 1 to kn, is a set of independent random variables. And the distribution of u and j is given by this difference. And we know from this remark, and this is the hypothesis I will use in order to prove A and B, is that this sum is converging to S minus S prime. So we have u and j defined by this expression. They are independent, and we know that they converge to S minus S prime. And from this hypothesis, this condition, I will deduce A and B. And the strategy, so let me mention the strategy before I prove that. So here is the strategy of the proof. Well, first, I will prove that A and B, they hold for the sequence u and j. So I'll prove that A and B hold if we provided we replace x tilde and j by u and j here and there. So that will be the first step of the proof. And then I will deduce A and B for x and j tilde from this condition. So first I will prove A and B for u, and then I will prove that if A and B hold for u, they also hold for x tilde and j. So this is the strategy of the proof, which I will now present. So, of course, here, I forgot to say, but let me mention that we want to prove this for all n larger than 1. Okay? For all. I think it was implicit, but let me make it explicit now. And what I want to observe is that if you want to prove that for all n, it's enough to prove that for all n larger than n0. Because if it holds for all n larger than n0, for n from 1 to n0, this is clearly bounded by 1, so you get bounds here, and you can just change the constant c delta in order to make this inequality to hold for all n, and not only for n larger than n0. And the same thing here. If it holds for all n larger than n0, well, you can just change your constant c0 in order to make it valid for all n, because, well, since you know that xn is bounded by 1, you can bound this expression by 1, and then it's a matter of changing the constant. So we'll prove that these two bounds hold for all n. And as I said, this proof is divided in two steps. Step 1 is to say that, well, the proof, these A and B hold for u and j, for the sequence u and j. So remember, and let me write it here, that u and j, it's equal to x and j minus x and j tilde prime. So I want to prove that A and B hold for the sequence u and j. And we have seen in the first part of the proof that if I want to prove A and B, it's enough to show that for all t positive, there exists a finite constant ct such that if I take the sum from 1 to kn of the expectation of 1 minus cosinus t u and j, that this is bounded by ct, And if I take, and this is for all t less or equal than t, and for all n larger than 1. So if I'm able to show that for all t, there exists a finite constant ct, such that this sum, it's bounded by ct for all t bounded in absolute value by t and for all n, then I can derive a and b for the sequence u and j. So my goal here is to prove that this inequality holds. So this is step 1. So I will erase this condition and I will derive it starting from the assumption that the sum of, so what we know is that the sum of u and j, it's converging to some distribution s minus s prime. So since this is true, we know by this convergence in distribution that the characteristic functions converge. So we know that the characteristic function of the sum of u and j of t converge to the characteristic function of s minus s prime of t. Well, since u and j is a symmetric, we know that this characteristic function takes only real values as well as this one. And we also know that this convergence is uniform over compact sets. So now I know that fs minus s prime of t, it's continuous, and at 0 it's equal to 1. So I can obtain an interval minus t0, t0, for which fs minus s prime of t, it's larger, say that 1/4 for all t, or let's say 1/2 for all t bounded by t0. Right, since phi it's continuous and it's equal to 1 at 0, we can obtain an interval around the origin in which the characteristic function is larger than 1/2 in this interval. And since this sequence it's converging uniformly in this interval, well, we can find n0 larger than 1 such that this expression phi u n j of t, it's larger than 1/4 for all t less than t0. Right, since the convergence is uniform, and since this one is larger than 1/2, well, for n sufficiently large, this function will be bounded below by 1/4 uniformly in this interval. So this is this holds for all n larger than n0. That's fine. So this is what we know. Now take a logarithm on both sides. These are a real number. So we know that log of 1/4, it's less or equal than the log of phi u n j of t. Now, the sum of u and j. Now we know that these random variables are independent, so this is equal to the sum of the log of, or maybe, I'm sorry, let me go back here and just use that 1/4. It's bounded by the product. So here, the random variables, instead of taking logarithms, I won't do that. I just take the product of phi u n j of t. Sorry about that. Now, I want to estimate this expression, and for that, I will write phi, which is a real number, as z. So maybe I used z, so let me call that y. So y will be standing for phi u and j of t. And what I will do, it's y, it's a number between 0, it's a real number between 0 and 1. So I will write that as 1 minus 1 minus y. Okay, this is fine. You wonder why I'm doing that, because now I want to use the inequality that 1 minus x, it's less or equal than minus exponential minus x. So this holds for all x positive. 1 minus y, it's positive, so it's okay. And now let me use this inequality to say that the exponential of y, so here x, it's 1 minus y, so this is bounded by exponential minus x, which is minus 1 minus y. Or, as the same, this is exponential y minus 1. So I want to use the bound that y, it's less or equal than exponential y minus 1 in this inequality. So if I do that, I will bound this product by the product in J of exponential phi u n j of t minus 1. And now, since the product, let me rewrite this expression as exponential of the sum, phi u n j t minus 1. So up to now, we proved that 1/4, it's bounded by the exponential of this expression for all t smaller than t0 and for all n larger than n. And now at this point, let me take the logarithm. So I get that logarithm minus logarithm of 4, it's less or equal than the sum of phi u n j of t minus 1. And let me multiply this inequality to get at the end that the sum. So let me multiply this inequality by minus 1 to get the following bound, that 1 minus phi u n j of t, it's less or equal than log of 4. And this is a constant, right? So we know that this sum, it's bounded by log of 4 for all t less or equal than t0 and for all n larger than n0. So that's the first bound, and we will start from this bound in order to prove, to get a bound on the cosinus. Well, so let me remind you what is the phi of u and j of t. So here you have to remember that since u n, it's a symmetric random variable, this is a real number, so the imaginary part vanish, and we only have to consider the real part of the characteristic function. So this is telling me that j of, so let me write it, let me go it very slowly, expectation of exponential I t u n j, that this is bounded by a constant c0, which is log of 4, but that is not important. And here, as I said, well, we know that since u and j is symmetric, that the imaginary part of this expression of this expectation vanish, and therefore we need only to consider the real part. And from that we get, what is the real part? The real part, it's you replace exponential I by cosinus, so you get that the exponential, placing the 1 inside, that the exponential of 1 minus cosinus t u n j, that this is bounded by c0. And this holds for all t less than t0 and for all n larger than n0. So this is the bound we prove up to now. And as I said, now I can replace n0 by 1 by changing this constant c0, because, well, this expression, it's bounded by 1, so the sum, it's bounded by kn. So if I replace c0 by a sufficiently large constant, I can make this inequality hold for all n. So this is what we know up to now, that for all n larger than 1, this sum is bounded by C0. Now it's easy to complete the proof. We did that many, many times, but I will repeat it here once again. So we know that 1 minus the cosinus of 2s, that this is bounded by 4 times 1 minus cosinus s. So since this inequality holds for all t smaller than t0, if I take now a t smaller than t0, I have a bound for 1 minus cosinus t un, and from that one I can get a bound for 1 minus cosinus 2 times t. So I can extend this bound by multiplying this constant by 4 from this interval to the interval 2t0. And if I repeat that many, many times, well, a certain finite number of times, I can extend this inequality from this interval to any interval I wish. So that proves what I claimed, that for all t, there exists a finite constant Ct such that the sum in J of the expectation of 1 minus cosinus t unj, it's bounded by Ct, and this holds for all t bounded by t0 and for all n larger than 1. So I just proved this inequality, and from this inequality we have seen in the first part of the proof that we can deduce a and b for un in place of x tilde. So now we proved, up to this point, we proved that a and b are in false if we replace x tilde by un. And the second step in this proof will be to show that if it holds for un, then it holds for, if a holds for un, then it holds for x tilde. If b holds for un, then it holds for x tilde. So this is what's coming next. So now let's turn to the second step of the proof. So step 2a. So assuming that this condition holds for un, and I will prove it for x unj, and I will prove it for x and j tilde. So we know that for all x there exists a constant c delta, such that the sum of unj larger than delta, it's bounded by c delta. So I have a constant c delta which is larger than this probability. So I'll take here, in order to finish with delta, I'll take here delta over 2. So I know that given that delta, I fix a delta, I consider delta over 2, by these conditions for un, I know that there exists a constant such that this sum is bounded by c delta. So what is, so let me just remind you what is u. Well, it's u, it's written here, so that this is x tilde nj minus x tilde nj prime. And here, instead of getting upper bounds, we'll need lower bounds. So we are not very much, at least I'm not very used to do that, but here this is quite simple. So this is certainly bounded below by the probability. So I'll introduce that x tilde nj prime, it's less than delta over 2. So this is, of course, this probability is bounded by this one, because I'm introducing here an extra condition. Now, what I claim is that, well, if xn it's less than delta, if x tilde n it's larger than delta and x tilde it's smaller than delta over 2, then xn minus xn prime it's larger than delta. So what I'm saying is that if xnj tilde it's larger than delta, so if I take xnj larger than delta and x prime bounded by delta over 2, then the difference has to be larger than delta over 2. I guess this is clear, and therefore this probability it's smaller than this one, so we have here again a lower bound. Right? It's clear that this set is contained in this set. Well, I can use at this point the fact that these random variables are independent to say that this probability it's equal to the product of the probabilities. And here, since x tilde has the same distribution, x tilde prime has the same distribution as x tilde, I can just erase the prime. So this is what I proved up to now. And at this point, I will use the fact that the sequence x tilde is uniformly negligible, the condition un. So the condition un was telling us that for all epsilon, the probability that x n j tilde it's larger than epsilon, that the maximum in j of this quantity it's converging to 0. So this means that this maximum it's bounded by 1/2. So let me take here epsilon equal to delta over 2. And so this maximum is converging to 0. So there exists n0, such that if n is larger than n0, then this maximum is bounded by 1/2. If this maximum is bounded by 1/2, this means that the probability that x tilde nj it's less or equal than delta over 2, that this is larger than 1/2. Right? If this probability is bounded by 1/2, then the complement needs to have a probability larger than 1/2. So this probability it's larger than 1/2 for all j, provided n it's larger than n0. So if I take here n larger than n0, I can use the fact that these probabilities are larger than 1/2 to say that this probability it's bounded by 1/2 times j of the probability that x tilde n j it's larger than delta. And this is exactly the bound we need, right? Now, this is condition A for the sequence x tilde n j. We started saying that this expression was bounded by a constant, now which depends on delta. Now we have that this sum it's bounded by the same constant multiplied by 2, provided that n it's larger than n0. So we proved that for all n larger than n0, but we can extend this inequality to all n by changing the constancy delta. So this shows that if condition A holds for the sequence u and j, it also holds for the sequence x tilde and j, which completes the proof of step 2a. So to conclude the proof, we need to prove step 2, in which step 2 consists in proving that condition B holds for x tilde, provided it holds for u and j. So I'm assuming that B holds for u and j, and I will derive it for x. And I will here assume that condition B holds for u and j with this one replaced by a 2. That's a very simple, it's very simple to derive this inequality with a 2 in place of a 1. You just can go in the proof and check that it's easy to transform the proof, to modify the proof in order to get a 2 in the place of 1. I will give details in the notes just to make sure that everything has been proven correctly. So let me assume that there exists a finite constant, C0, such that C0 is larger than the sum for x tilde, and x tilde now, remember, it's u and j square, the characteristic function that u and j it's less or equal than 2. So I'm assuming this condition, and I want to derive it for x. So here again, I will obtain a sequence of lower bounds instead of upper bounds. So let me first replace u by its value. So u, it's x n j tilde minus x n j tilde prime square, the characteristic function that x n j minus x n j prime, it's bounded by 2. Now I need lower bounds. So I'll start by adding a condition in this expectation, and this will, of course, provide me a lower bound. So I won't touch the square, but here I will introduce the characteristic function that x n j tilde prime, it's bounded by 1. So I'm just introducing inside the expectation a new condition, which is the condition that the variable x n j prime, it's bounded by 1. And this, of course, gives me a lower bound. Now, what I claim is that if I know that x prime, it's bounded by 1, and x, it's bounded by 1, then the difference, x minus x prime, it's bounded by 2. And therefore, this expression, it's larger or equal than the sum of the expectation of x n j tilde minus x n j tilde prime square, the characteristic function that x n j, it's bounded by 1, the characteristic function that x n j prime, it's bounded by 1. So let us check, now that everything is written, indeed if x and x prime are bounded by 1, then the difference, x minus x prime, it's bounded by 2. So this expectation, it's bounded by this one. At this point, I want to use the fact that these random variables are independent. So what I will do is I will first integrate it over x and then over x prime. So this second expectation, I'll put a prime here just to remind you that I'm integrating that with respect to x prime, and while the first one, it's an integration with respect to x. Well, here I can take out, since I'm integrating first with respect to x, I can move out of the expectation this prime nj. So this is fixed inside, it's a constant inside the first expectation. And here what I get is that this is xn j minus xn j prime square, and the characteristic function, the indicator function that x prime and j, it's bounded by 1. So in this, remember, here I'm integrating only with respect to x and j, and here then I'm integrating with respect to prime. So this is a constant because I'm here integrating with respect to x, so that's a constant, and this constant, it's bounded by 1. So that's clearly bounded below by the infimum. So remember, here x prime, it's fixed because I'm integrating with respect to the other variable, and x prime, it's bounded by 1. So this is clearly larger than the expression in which I here fix y, and I take a y bounded by 1. Right, so here I'm fixing x prime, and I'm integrating with respect to x. And now, since x prime is bounded by 1, I'm saying that this expectation, it's bounded by this expectation if I take the infimum over all y bounded by 1. And so remember, here I started from a constant. Now, by independence, what I get is that, well, this is equal to the probability that here the only dependence on x prime is this one, so this is the probability that x prime it's less or equal than 1 times the expectation, the infimum in y bounded by 1 of the expectation of x n j minus y square, and the indicator that x n j it's less or equal than 1. Right? So by using independence, so the measure here, it's a product measure, so I can move this expectation, which does not depend on x prime anymore, out and have that this is equal to this infimum times this probability, simply because, well, these variables are independent, and therefore the measure, it's a product measure. Now, here I claim that if n is larger enough, I can repeat the argument with delta equal to 1, saying that, well, since the sequence x, so first I can remove the tilde because the distribution is the same, and then I can use the same argument I used in step 2a to say, well, that since the sequence satisfies the un condition, these probabilities are bounded below by 1/2, provided n is sufficiently large. So this is larger than 1/2 if n is larger than n0, so there exists an n0 for which these probabilities uniformly in J are bounded below by 1/2, provided n is sufficiently large. And what I get, it's the sum in J of the expectation of this, the infimum of this expectation. But let's compute this square. So in this square, I get the expectation of x n j square minus 2 times y x n j plus y square. But since I want a lower bound, I will just forget this positive term. So here I had plus y square of this indicator of the set that x and j, it's bounded by 1. But this is bounded by the same expression without the y square. So I'll just erase the y square and keep the first two terms. So let me continue in my sequence of lower bounds, and remembering that this is bounded by C0. So now I want to consider separately these two terms. So the first one does not depend on y, so this is for the moment equal to 1/2 of the sum of the expectation x and j, but there are tildes which I now forgot. Square the indicator that x tilde and j it's bounded by 1, and then plus the infimum for y bounded by 1 of minus 2y, the expectation of x and tilde j chi x and tilde j less than 1. So here I separated these two terms. The first one, there's no y, so I get it here. And then there is a second one, which is the infimum of minus 2y bounded by 1. And, well, if I want a bound here, a lower bound, I'll just say that this is bounded by minus 2 times, since y is bounded by 1, this is minus 2 times the absolute value of this expression. Right? This infimum is certainly without the minus sign. This infimum is certainly bounded by this expression, right? Because, well, y it's bounded by 1, so this expression it's bounded by its absolute value, so this expression is bounded by that one. So with the minus sign, this means that this is bounded below by this expression, and therefore this whole expression, what I proved is that this is bounded by 1/2 the sum in j of this expression minus this one. And here you can recognize, if I write it correctly, that what appeared is a tilde and j. So this is the absolute value of a tilde and j. So what we have is that this expression, it's bounded below by 1/2 of the sum in j of the expectation nj square, the indicator of the set that x and j is bounded by 1, which is the first expression, and then I have minus 2, which cancel with this 1/2, so minus 1 times the sum in j of a and j. So up to now we proved that a constant it's bounded below by this difference. And we are ready to conclude. Now let's use the fact that we know that a and j tilde it's bounded, so this is one of the reason. This is the reason why we replaced x by x tilde, that the absolute value of a tilde and j it's bounded by the probability that x and j it's larger than 1/2 times a constant c0. So I will use this inequality to say that this is bounded by 1/2 times the sum of the expectation x and j tilde square, the indicator that x and j tilde it's bounded by 1, minus, so a and j is bounded, so we get a minus, so this is bounded by c0 times these probabilities. So what we proved is that, and this is a new constant, right? So let me call it constant 1, not to mix it with this constant which we started from. So what we proved that there is a constant which is bounded below by this difference. So that tells me, that implies, this implies that 1/2 of the sum of the expectation of x and j tilde square, the indicator that x tilde and j is bounded by 1, that this is smaller or equal than the constant C0, which we started from, plus C1, the sum that the probability of x and j tilde is larger than 1/2. By part A, we know that this is bounded by a constant, so this is bounded by a constant C2, and this is exactly what we wanted to prove. So now remember, we used part A to complete the proof by showing that this sum is bounded by a constant C2. So we proved this inequality for all n larger than n0, but as I said at the beginning of this lecture, we can now change the constant in order to include all n's from 1 to n0. So that proves B and completes the proof of the main result of this second part of the proof.